Welcome to the deep dive. If you're constantly trying to keep up with the lightning-fast world of artificial intelligence, well, you're definitely in the right place. Today, we're cutting straight through the noise to get you truly well-informed on the very latest in AI research. You've sent us an incredible stack of sources, the AI Paper Weekly from Xiao's Substack, fresh from July 19th, 2025.
Yeah, it's quite a collection. A really exciting snapshot, actually. Shows us exactly where cutting-edge AI is headed right now. From groundbreaking new architectures to some surprising insights into how these models actually think. Our mission, really, in this deep dive is to pull out the most important nuggets of knowledge from these 19 papers. We want to help you grasp the core innovations, their broader implications, without getting sort of bogged down in every single technical detail.
Absolutely. Think of it as a guided tour through some of the most, surprising breakthroughs in AI this week. So let's just jump right in and unpack some truly fascinating research. All right, the first paper we're diving into introduces something called energy-based transformers, or EBTs. The big headline here is they enable system-to thinking capabilities. And through unsupervised learning, that sounds like a pretty big deal.
Oh, it absolutely is. What's really revolutionary about EBTs is how they approach problem solving. Unlike traditional models that are often just trained to predict the next thing, like the next word, EBTs learn to verify their own outputs. It's imagine a ball rolling down a complex landscape, right? It'll naturally settle into the lowest point of energy. EBTs use a similar idea, an energy function, to find the most harmonious, the most consistent state between an input and a prediction. This means the model isn't just spitting out an answer, it's actively trying to find the most correct answer by minimizing this internal energy of inconsistency, you see.
So it's not just predicting, but it's also checking its own work, refining its internal understanding. That's incredibly clever. What kind of performance gains does this actually bring?
Precisely. Yeah, this novel architecture allows for predictions through a process called gradient descent-based energy minimization, essentially. It's like an iterative refining process. And this leads to really superior scaling. They achieve up to 35% higher scaling rates compared to existing models like Transformer Plus across various factors: data size, batch size, model depth, parameters, FLOPs.
Wow.
You can actually see this iterative thinking process play out. They show it in Figure 2, applying it to both text and video tasks. For instance, on language tasks, they reported 29% better performance improvement, specifically tied to these system-to thinking capabilities.
29% is huge.
It is. And what's more, they even outperformed diffusion transformers, which are, state-of-the-art in image generation on image noising tasks. And with fewer computational steps, fewer forward passes.
That's a massive leap then in both efficiency and capability, especially since it's all unsupervised. It's like the model is teaching itself to be more precise.
Indeed. The methodology applies the Energy-Based Models Framework, EBMs, to transformers, and the fact that it works across both discrete data like text and continuous data like visuals, all without direct human supervision. Well, that's a game changer. This really signifies a paradigm shift. If you look at their Table 1, which compares architectures on cognitive facets, EBTs really stand out. They excel in things like dynamic compute allocation, modeling uncertainty, and prediction verification because they're designed for this deeper iterative reasoning. It really has the potential to revolutionize how AI handles complex multi-step reasoning tasks.
Okay, next up we have HNet. This is a hierarchical network tackling something pretty fundamental: how models break down information. It replaces traditional tokenization with what they call dynamic chunking. Why is getting rid of fixed tokenization such a big deal for AI?
Right, this really hits at a core challenge for true end-to-end learning. Think about how we usually feed data to AI, right? We break it into tokens, like words or parts of words. But this traditional tokenization often forces models into a fixed vocabulary. And that can be rigid, inefficient, and it really struggles with diverse languages or, say, raw data like DNA sequences where words aren't clearly defined. HNet learns to segment data dynamically. It adapts its chunking strategy based on the content and the context. It's like the model instinctively knows how to group information most effectively, rather than just relying on these predefined rules.
So it's more like how we naturally parse speech or understand the flow of a paragraph, not rigidly splitting it into predefined words, but recognizing meaningful segments as they appear.
Exactly that. The key innovation is that dynamic chunking mechanism itself. HNet, as you can see in their Figure 1 overview, essentially replaces the entire conventional pipeline. Tokenize, run the LM, decokenize with a single unified model. You have these chunking and dechunking layers with routing modules, downsamplers, smoothers, upsamplers.
And the results?
Compelling. It outperforms strong transformer LMs, often with less compute. For example, It showed nearly a 4-fold improvement in data efficiency on DNA sequences.
Wow, 4 times.
Yeah. And significant strides on languages like Chinese and also on code, which are notoriously difficult for fixed tokenization methods, these weak tokenization domains. This is a fundamental step towards AI models that can truly process raw, unstructured data in a more natural, robust way.
Okay, this next paper dives into reward modeling. Super crucial for training intelligent AI agents to do what we want them to do, right? They've got this novel perspective, formulating it as a policy discriminator. What's so different about this polar method?
Well, if we zoom out a bit, traditional reward models often rely on an AI giving an absolute score to an action or outcome. Is it good, bad, somewhere in between? Polar takes a different approach. Instead, it learns to discern identical policies from different ones. It's not saying this policy is great, but more like this policy is more like what we want than that other one.
Right.
It means it captures relative differences in rankings between policies. And that's incredibly powerful for guiding an AI agent in complex, nuanced scenarios.
Yeah.
Figure 1 in their paper actually compares it nicely to other methods.
So it's not just good or bad, but better or worse compared to another policy. That seems like a much more flexible way to teach an AI.
It really is. The core contribution is this novel perspective and the polar pre-training method itself, which is designed to be highly scalable. You can see the 3 stages in their figure 2. Pre-training, fine-tuning, and then usage in RFT. And it substantially outperforms traditional methods that aren't pre-trained this way. They saw reward model performance improve significantly, like on STEM tasks, performance jumped from about 55% up to 81%.
That's a massive jump.
Huge. And what's particularly exciting for the future of large-scale AI is that their scaling experiments show a very clear power law relationship between computation and performance. High correlation, like 0.99, meaning as you put more resources into polar, you get predictable, strong gains. This offers a really promising direction for developing truly general and powerful reward models for LLMs.
Okay, moving from how agents learn what's good, we now look at how LLMs explore possibilities, specifically for reasoning. This paper introduces FR3E. It's a framework that identifies high-uncertainty decision points to improve reasoning in LLMs. What problem is FR3E trying to solve here?
What's fascinating here is how it addresses the sort of blind spots in an LLM's exploration. When an LLM tackles a complex reasoning task, like a tricky math problem, it can struggle to know where it's getting stuck or why a particular path isn't working out. FR3E solves this by identifying where the model is most uncertain, or, technically speaking, has high entropy decision points. Figure 2 shows examples of tokens with high average entropy, and then it performs targeted rollouts or explorations specifically in those uncertain areas.
Right.
It's like giving the model a focused tutor just for its weak spots. It generates this semantically grounded intermediate feedback that guides it, but without needing dense, step-by-step human supervision, which is a huge advantage.
So it helps the model figure out where it's most confused and then gives it specific, tailored help right there. That sounds incredibly efficient for training.
It is very efficient. The FR3E framework, you can see the overview in their figure 1, has 2 main stages. First, return helps pinpoint those high uncertainty positions, and then Entropy-Eliciting Explore launches those targeted explorations. Their key contributions are this structured framework and the ability to generate meaningful feedback without heavy supervision. And this leads to much more stable training for LLMs, especially in what's called reinforcement learning from verifiable rewards, or RLVR.
And the result?
The result. These models produce longer, more coherent responses and dramatically increase the proportion of fully correct solutions. They show this particularly on challenging mathematical reasoning benchmarks like AME24. Identifying those uncertain tokens is really key to this targeted improvement.
Okay, this next paper, it's got a provocative title. Machine bullshit. It introduces a framework to characterize LLM's emergent disregard for truth. So what exactly is machine bullshit, according to the authors, and why is this different from just, hallucination?
Yeah, that title definitely catches the eye, and it raises a really important nuance in understanding AI's untruthfulness. They build on the philosopher Harry Frankfurt's definition. So machine bullshit isn't about generating outright falsehoods by mistake, which is often what we mean by hallucination. Instead, it refers to statements made by the AI with an indifference to their truth value.
Indifference.
Okay. It's not that the AI intends to lie or is necessarily mistaken. It simply doesn't prioritize factual accuracy in that moment. It's generating text that sounds plausible, perhaps persuasive, regardless of truth. They even propose a bullshit index to quantify this indifference. And they've identified 4 key forms: empty rhetoric, Paltering, which is selectively omitting key information, weasel words, so vague language and unverified claims. Their figure 1 gives some good examples.
So it's not about being factually wrong necessarily, but about not caring whether it's right or wrong, just generating plausible sounding text. That's subtle, but a really important distinction for assessing AI reliability, isn't it?
It absolutely is. And their empirical evaluation shows some, frankly, concerning trends. Fine-tuning with RLHF learning from human feedback actually significantly increases machine bullshit.
Really? RLHF increases it.
Yeah. And inference time chain of thought prompting, COPE, which we often think improves reasoning, well, it notably amplifies empty rhetoric and paltering. They saw a lot of machine bullshit in politically sensitive contexts, with weasel words being the dominant strategy there. This research pushes us beyond just hallucinations or even sycophancy to understand deeper, maybe more insidious mechanisms behind LLM's untruthful behaviors, and that's crucial if we want to develop truly truthful and reliable AI systems.
Speaking of how LLMs reason, this next paper surveys latent reasoning. We often hear about chain of thought, CODI, right, where LLMs sort of show their steps. But what's this latent reasoning, and why is it potentially so powerful?
Right. What's fascinating here is the sheer difference in, let's call it, processing capacity or bandwidth. When an LLM uses explicit chain of thought, it's essentially thinking out loud by generating discrete tokens, words, right? This is like a very slow, limited internal conversation. They estimate maybe 15 bits of expressive bandwidth per token.
Okay.
Latent reasoning, however, performs multi-step inference entirely within the model's continuous hidden state. Think of that as the model's internal unconscious workspace. This hidden state can be enormous. For a typical model, it might be around 40,960 bits for a single hidden state.
Wow, that's a huge difference.
Massive difference. You can see this contrast clearly in their figure 1. It means latent reasoning can leverage a far richer, more complex internal representation, a much, much broader bandwidth for thought.
So it's like the model is doing its deep, complex thinking internally without needing to speak or spell out every single step in words. It's keeping its elaborate thought process kind of internal.
Exactly. This paper is actually the first comprehensive survey on this emerging field. It explores various approaches, activation-based recurrence, hidden state propagation, even touches on cutting-edge ideas like infinite depth latent reasoning using masked diffusion models. This survey clarifies a very new area, providing a roadmap for how we might enhance LLM cognition by tapping into the full expressive power of their internal representations. And this could lead to more robust, generalizable reasoning, maybe even globally consistent and reversible reasoning processes, meaning the AI could potentially unthink or backtrack its steps perfectly.
Our next paper shifts gears to world models in AI. This sounds like something straight out of science fiction. What are world models exactly, and why are these authors critiquing the current approaches?
Yeah, world models does sound sci-fi, doesn't it? If we connect this to the bigger picture, world models are essentially algorithmic simulations or surrogates of the real-world environment. Think of it like your own mind, imagining possible outcomes before you act. It's kind of an internal world model. Figure 1 in the paper uses a human analogy for this. This paper critically examines existing approaches, and it argues that their primary goal shouldn't just be simple prediction, like, say, predicting the next frame in a video. Okay. Instead, they argue, world models should be able to simulate all actionable possibilities of the real world, specifically for purposeful reasoning and acting. They're saying these models need to go beyond just foreseeing. They need to simulate for the purpose of decision-making. Figure 2 outlines an agent environment framework related to this.
So it's about making AI models capable of thinking through all potential consequences of their actions and using that simulation to decide what to do, not just predicting what might happen generally. That's a much more active, purposeful role.
That's spot on. Their key contributions include this comprehensive critique and a redefinition of what a world model's goal should be. They propose a new general-purpose world model architecture. It's hierarchical, multi-level, uses mixed, continuous, and discrete representations. Really complex stuff. This allows for incredibly nuanced and detailed internal simulations. They even present an outlook for what they call a pan-AGI system, physical, agentic, and nested, that could be enabled by such a model. This paper offers a fresh, actionable perspective, guiding future research toward building far more capable AI systems that can truly understand and interact with the complexities of the real world. It's laying profound groundwork for future AGI.
Okay, this title definitely grabbed my attention, Humanity's Last Exam. What is this exam, and how is SciMaster taking it on?
What's fascinating here is the sheer ambition, right? Leveraging AI agents to dramatically accelerate scientific discovery. Humanity's Last Exam, or HLE, is a notoriously challenging benchmark. It's designed to test an AI's ability to tackle complex, open-ended scientific problems that might normally take human researchers years. This paper introduces SciMaster. It's a foundational architecture that tries to emulate how human researchers work by flexibly interacting with external tools, like running simulations or analyzing data. They conceptualize code not just as programming, but as an interaction language for these AI agents, allowing them to truly manipulate and experiment with information.
So SciMaster is kind of like an AI scientist using tools and writing code to actively solve these incredibly hard scientific problems.
Exactly. The core SciMaster architecture enables this advanced tool-augmented reasoning. And they didn't stop there. They also introduced SciMasters, which is a scattered and stacked agentic workflow. It's designed to enhance both the breadth and the depth of the AI's reasoning, sort of like having a team of specialized AI agents collaborating.
And how did it do on this last exam?
The results are, well, astounding. SciMaster set a new record on HLE with a score of 32.1%. Now, to put that in perspective, their Figure 1 shows this clearly. It surpasses top models from OpenAI and Google Deep Research, which scored around 26–27%. This is a significant leap, breaking the 30% threshold for the first time on this benchmark.
Wow.
This work doesn't just improve performance, it offers deeper insights into complex task solving. It accumulates valuable experience for building truly general-purpose scientific AI agents. It's paving the way for accelerating scientific discovery on a potentially grand scale.
Okay, from scientific agents, let's move to vision language models, VLMs. This report introduces Skywork R1v3, which pioneers a new approach to visual reasoning. What makes it so advanced?
Yeah, this raises a really important question. How do we efficiently get complex reasoning skills into these multimodal models? Skywork R1v3 manages to effectively transfer sophisticated reasoning skills, think mathematical or logical reasoning, from text-only LLMs over to visual tasks. What's truly impressive, I think, is that its strong performance primarily comes from an elaborate post-training reinforcement learning framework.
Post-training RL.
Exactly. This means it activates and enhances reasoning ability after the initial, more general training without needing additional, very costly pre-training specifically for visual reasoning. This is a crucial technical innovation, could save immense resources.
So it's essentially taking an LLM's brain for text and teaching it to apply that same kind of sophisticated thinking to images, but doing that refinement after the main training. That sounds incredibly efficient.
Precisely. And beyond the RL-powered post-training, a key contribution is a novel reasoning indicator they developed. It's the entropy of critical reasoning tokens.
Yeah.
Basically, a way to measure uncertainty during reasoning, which helps them select the best model checkpoints during that RL training phase.
And the results?
Skywork Edge R1v3 achieves state-of-the-art results, 76.0% on the demanding MMMU benchmark. They say that matches entry-level human expert capabilities. You can see this in their Figure 1 benchmark comparisons. This RL approach enables even their 38 billion parameter model to rival top closed-source VLMs, and it successfully transfers mathematical reasoning skills to other subject-related visual tasks. It genuinely represents a significant leap in multimodal reasoning capabilities.
Right. When we talk about large models, Google's Gemini family always comes up. This report introduces Gemini 2.5 Pro and Flash. What makes this new generation so impactful for AI capabilities? What's the big step up?
Well, if we connect this to the bigger picture, the Gemini 2.x family is really designed to cover the entire spectrum, the whole Pareto frontier of model capability versus computational cost. Gemini 2.5 Pro, for example, is Google's most capable model to date. It truly excels in multimodal understanding, meaning it can process and understand incredibly diverse data inputs. We're talking about the ability to process up to 3 hours of video content.
3 hours of video? Wow.
Yeah, and handle over 1 million tokens of long context. That's like reading hundreds, maybe thousands of pages simultaneously. And it unlocks entirely new, powerful agentic workflows where the AI can plan and execute really complex multi-step tasks. They offer a whole family now, as shown in their table: 2.5 Pro, 2.5 Flash, 2.0 Flash, even a flashlight. So developers have a range of options depending on whether they need raw power or cost efficiency.
Processing 3 hours of video is just incredible. What kind of real-world results are they seeing across this family of models, especially with that Pro version?
It's a massive leap forward. Gemini 2.5 Pro demonstrates exceptional reasoning and coding abilities, including understanding entire code bases, which is a huge challenge. Gemini 2.5 Flash, on the other hand, provides excellent reasoning, but at significantly reduced compute cost and lower latency. That makes it ideal for applications where speed is critical, right? You can see this trade-off visually in their Figure 1 cost-performance plot. What's impressive is that despite these advanced capabilities, they've maintained robust safety metrics across the series. The unique blend of massive context windows, true multimodality, and advanced reasoning in Gemini 2.x series, it really pushes the boundaries of complex agentic problem solving, sets a new standard for AI assistants that can tackle real-world, messy situations.
Okay, building on that multimodal understanding, this next paper addresses a major challenge: applying reinforcement learning to long videos. How do they enable vision language models to reason over, like, hours of content? Because that's a huge leap from just short clips.
Yeah, it's a huge leap. And what's fascinating here is their comprehensive full-stack approach. They didn't just build a model, they built everything around it. They've tackled this monumental task with three key components. First, a new massive data set called Long Video Reason. It's got 52,000 question-answer pairs specifically designed for long video understanding. Figure 3 shows the data distribution.
Okay, bespoke data.
Exactly. Second, a clever two-stage training pipeline. It combines chain-of-thought supervised fine-tuning, co-ESFT, with reinforcement learning. And third, they created a novel training infrastructure they call Multimodal Reinforcement Sequence Parallelism, or MRSP. That's all about achieving unprecedented efficiency for this very specific, very demanding task.
So it's not just the model itself, but also developing the right data and a super efficient training system to handle this massive scale. That makes sense.
Exactly. That MRSP infrastructure is a huge technical win. Their Figure 1 shows it achieves up to a 2.1 times speedup in RL training for long videos. And crucially, it avoids the dreaded GPU out-of-memory issues that often plague large model training, especially with long sequences.
Right. And the model itself, LongVilla.
Their model, LongVilla R17B, achieves really strong performance on long video QA benchmarks. It either outperforms or matches Gemini 1.5 Pro across various reasoning types: temporal, goal-oriented, spatial tracking, plot following, you name it. Their Figure 2 actually shows some cool examples reasoning over a full football game, a poker match, tracking things spatially in long videos. This work represents a really firm foundational step towards enabling VLMs to truly understand and reason over hours of real-world content. Opens up vast potential applications.
Okay, this next paper takes us into specialized AI medical vision language models. It introduces MedGemma. Why is a dedicated medical foundation model so important? Why not just use a general VLM like Gemini or Skywork?
Right, this raises a critical question about generalization, especially in highly specialized and frankly sensitive domains like medicine. Medical data is incredibly nuanced, isn't it? It often requires very specific knowledge, and the ability to interpret complex visuals, think X-rays, pathology slides, CT scans. MedGemma is a new collection of medical VLM foundation models. They're built on Google's Gemma models, the 34B and 27D versions. And it demonstrates truly advanced medical understanding and reasoning, specifically tailored for medical images and text. The reason it's so important is that it significantly exceeds the performance of similar-sized general-purpose generative models when applied to medical tasks. And it even approaches the performance of models that were specifically built for just one narrow medical task.
So it's not just a general-purpose VLM applied to medicine, but it's fundamentally built for it, understanding the unique complexities of medical data from the ground up.
Correct. A key contribution is the MedGemma model collection itself. And a crucial component, as illustrated in their Figure 1 overview, is MedSiglip. That's a medically tuned vision encoder that powers MedGemma. This specialized encoder performs comparably to even highly specialized medical image encoders built just for one thing, and MedGemma itself. It achieves significant improvements on unseen medical tasks, showing great out-of-distribution performance.
Like what kind of improvements?
For example, a 2.6% to 10% improvement on multimodal medical QA, and a really impressive 15.5% to 18.1% boost on chest X-ray classification compared to general models. And further fine-tuning enhances its performance even more. It leads to substantial error reduction in things like electronic health record information retrieval, and achieves state-of-the-art comparable results in specific tasks like pneumothorax detection and histopathology classification. MedGemma really provides a robust foundation for medical AI, accelerating research and development.
Okay, back to reinforcement learning. This paper introduces Q-chunking for improving RL algorithms, especially for those tricky, long-horizon, sparse reward tasks. What exactly is action chunking, and how does it help AI agents in complex environments?
What's fascinating here is the core insight. Instead of an AI agent predicting just a single immediate action like move left slightly, it predicts sequences of future actions. They call these chunks. Imagine a robot trying to assemble something complex. Instead of deciding move arm, then rotate wrist, than grasp part. The queue chunking approach might predict a whole sequence like pick up screwdriver and position.
Ah, okay, higher level actions.
Exactly. Higher level, temporally consistent behaviors. This fundamentally mitigates the exploration challenges you get in standard temporal difference, or TD-based RL, especially when rewards are rare. It leverages these consistent behaviors often found in offline data. It also leads to more stable and efficient TD learning because the model is thinking in larger, more coherent steps.
So instead of micromanaging every tiny movement, you're giving the agent these bigger goals or subroutines to execute, making it much more efficient for long multi-step tasks where you don't get rewarded often.
Precisely. The queue chunking method applies this action chunking idea directly to TD-based RL algorithms. Their figure 1 illustrates the mechanism how it enables fast value backups and uses these temporally coherent actions for exploration. It also shows the success rate improvements on the OG bench domains. It significantly outperforms prior offline to online methods on these challenging long horizon, sparse reward manipulation tasks in OG bench. Their key contributions are this novel queue chunking approach, improved exploration, and much more stable, efficient TD learning. It really offers a valuable recipe for enhancing RL algorithms, particularly for those tricky, complex tasks. Paves the way for more robust RL systems.
Okay, this next paper challenges a piece of conventional wisdom in training language models, namely that small batch sizes destabilize training. They're saying vanilla SGD can even work, even with a batch size of 1. This sounds like it could save a lot of compute, which is always a huge deal in AI.
Yeah, this really raises an important question about fundamental optimization efficiency. For years, the belief has been, you need large batch sizes, you need complex optimizers like AtomW, maybe gradient accumulation, to train these massive language models stably. These authors revisited small batch sizes. They went all the way down to a batch size of 1. And they found something quite surprising.
Which was?
They actually lead to stable training.
Yeah.
Not only that, they're more robust to hyperparameter choices, meaning less tedious tuning. And they achieve equal or even better performance per computational unit per FLOP. And here's where it gets really interesting and potentially practice-changing. They notably enable stable LLM training with vanilla stochastic gradient descent, plain old SGD, even without momentum.
Wow, vanilla SGD?
Yeah.
Seriously. This directly questions the necessity of all those complex optimizers or the common practice of gradient accumulation in many scenarios. You can see this in their figure 1 plot. A shows optimizer performance across batch sizes, and B shows the hyperparameter robustness. Small batches just look more stable.
So all those fancy optimizers and techniques that we kind of assumed were essential, they might not always be necessary if you just use a small batch size. That could simplify things enormously for many researchers, couldn't it?
That's the powerful implication. They found small batch sizes are consistently more robust to hyperparameter choices, less tuning effort. And the research strongly suggests that gradient accumulation, which is often used to simulate large batches on limited hardware, is frequently wasteful, especially when training on single devices or smaller clusters. This research provides truly valuable insights for optimizing language model training. It could lead to much more efficient resource utilization and simpler training setups. This is particularly beneficial for researchers and practitioners who might have limited access to massive computational resources. Okay, this paper provides an introduction to modern methods in associative memory, and it connects them to state-of-the-art AI like transformers and diffusion models. What exactly is associative memory? And why are we sort of circling back to it now in the age of giant LLMs?
Right. What's fascinating here is the foundational theoretical lens it provides. Associative memories historically think hot-field networks are recurrent neural networks. They were designed specifically to store and retrieve information based on content, not like a computer memory based on location. Think of it like your own memory, right? You recall a whole event just from a single smell or a snippet of a song. That's associative recall.
Okay.
This tutorial highlights how recent theoretical breakthroughs are offering fresh interpretations of how even modern AI networks, like transformers, actually compute, and how novel mathematical formulations, like Lagrangian formulations they discuss, are allowing us to design incredibly powerful distributed models that learn surprisingly useful representations by leveraging these associative memory principles.
So it's about how AI models store and retrieve information fundamentally. And we're finding new ways to apply these maybe classical concepts to today's cutting-edge architectures. It's like finding new life in old ideas.
Precisely. The paper offers a really accessible overview of these modern associative memory methods. It delves into the theoretical advancements regarding their information storage capabilities. And crucially, it explores the deep relationship between these classic associative memories and today's dominant architectures, transformers, diffusion models. Their figure 1.1 actually gives a nice visual. It shows how associative memory unifies association, memory, and error correction through an energy minimization framework. You see a query gradually refining itself towards a low energy or stable memory state. This tutorial effectively bridges the gap between classical models and modern AI. It offers valuable insights for researchers and practitioners to better understand, interpret, and maybe even design advanced AI architectures, especially when thinking about how models manage and recall vast amounts of information robustly.
Fine-tuning large models efficiently. Always a hot topic, especially as these models just keep getting bigger, right? This paper introduces SingLoRA. It's a reformulation of a popular technique called LoRA low-rank adaptation that promises more stable training and, incredibly, halves the parameter count. How does it achieve this, like, magic?
Yeah, magic is a good word for it, but it's clever math. This raises a really important point about optimization stability and parameter-efficient fine-tuning, or PEFT. So traditional LoRA uses two separate low-rank matrices, usually called A and B, to adapt a model's weights. The issue is the scale of these two matrices can be quite different, and that mismatch can sometimes lead to unstable training dynamics.
Okay, scale mismatch.
Exactly. SingLoRA is brilliant because it learns the weight, update the change to the original weights, as a decomposition of a single low-rank matrix multiplied by its own transpose. So instead of A times B, it's like L times L transpose.
Yeah.
This seemingly small change inherently removes those intermatrix scale conflicts because there's only one matrix. It ensures much more stable optimization. And yes, as a consequence of this structure, it roughly halves the number of parameters needed for the fine-tuning adaptation compared to standard LoRA.
That's a very elegant way to simplify and stabilize things. What kind of performance gains are they actually seeing in practice? Does it work as well?
It actually works better in their experiments and with fewer parameters. It's quite significant. On a language understanding benchmark called MNLI, using a Llamas 7B model, SingLoRA achieves 91.3% accuracy. That surpasses traditional LoRA, which got 89.1%, and even an improved version called LoRA Plus at 90.2%. And SingLoRA did this using only 60% of their parameter budget.
60% of the parameters for being results. That's impressive.
Very impressive. And for image generation, on a task called DreamBooth, it significantly improves image fidelity compared to other methods like Dora and LoRA, achieving a better Dino similarity score. Plus, this novel reformulation even provides a theoretical guarantee for stable feature learning within the infinite width neural network framework, which gives it strong academic backing. So yeah, SingLoRA offers a more stable, efficient, and effective method for fine-tuning large pre-trained models. Superior performance, fewer parameters, big win.
Okay, recurrent models, like the older RNNs and LSTMs, they're great for sequences, but they often struggle with length generalization, basically, performing well on sequences much longer than the ones they were trained on. This paper has a new hypothesis for why they fail, and surprisingly simple fixes. What is this unexplored states hypothesis?
Right. What's fascinating here is the core explanation they found, which seems quite intuitive once you hear it. They argue these models fail to generalize to longer sequences because they're only exposed to a limited subset of attainable internal states during training. Imagine a maze runner who's only ever trained on very short, simple mazes. They never learn the complex turns or dead ends or loops that appear in much longer, more convoluted mazes. The model simply hasn't seen enough of its own possible internal memories or hidden states during training to know how to handle significantly longer sequences where those novel states might arise.
Okay, that makes sense. Limited experience.
Exactly. Limited internal state experience. But the good news is they found incredibly simple training interventions that fix this. Things like initializing the model's internal state with a bit of random Gaussian noise at the start of a sequence, or taking the final hidden state from one input sequence and using it as the initial state for the next sequence. During training, they call this state passing. These simple tricks enable robust length generalization with minimal additional post-training steps.
So they're basically teaching the model to explore its own internal mind or memory space more fully during training just by nudging its starting point. That's quite an elegant solution.
It really is. You can literally see the effect in their figure 1. It plots perplexity, which measures how well the model predicts the next token against the token position. Normally, perplexity shoots up as sequences get longer than training. But with their state-passing intervention, it stays low, even for sequences way, way longer.
Or much longer.
With only 500 post-training steps, which is tiny, like 0.1% of the original pre-training budget, these interventions enable length generalization for sequences going from, say, 2,000 tokens up to 128,000 tokens. Orders of magnitude longer than their training context.
Wow.
This research provides crucial insights into why length generalization fails in recurrent models and offers incredibly practical, efficient solutions. It really improves their robustness and applicability for processing very long sequences, making them much more viable alternatives to transformers in certain scenarios again.
Okay, the Mamba architecture. It's been making waves as an alternative to transformers, especially for long sequences, right? But this paper introduces Differential Mamba. It's designed to address a problem. Apparently, standard Mamba sometimes overallocates its attention or its processing focus to irrelevant context. This leads to noisy intermediate representations. What's the fix they propose?
Yeah, this raises a really important question about refining these newer space-based architectures like Mamba. While differential design, which is basically a way of making models more selective about what information they process and pass forward, while that's helped transformers become more efficient, like in differential attention, simply adapting it naively doesn't work well for Mamba's unique structure. So they propose a novel differential mechanism specifically tailored for the Mamba architecture. It directly mitigates this problem of overallocating resources or attention to parts of the input sequence that aren't actually relevant for the current task. Essentially, it teaches Mamba to be more discerning about what it focuses on in the input sequence. It helps filter out the noise and concentrate on what's truly relevant for making the next prediction or understanding the context.
So it's like giving Mamba a highly refined filter, allowing it to be much more selective and efficient with its attention span, even though it doesn't use attention in the same way transformers do?
Precisely. That's a good way to put it. Their key contribution is this unique differential Mamba architecture. It specifically targets that issue of sequence models, including Mamba, sometimes getting bogged down by irrelevant context. They've empirically validated that it significantly enhances retrieval abilities in language modeling tasks. That means the model can pull out relevant information from long texts much more effectively. And it also consistently demonstrates better overall performance, like lower perplexity compared to vanilla Mamba. This work represents a significant improvement to the Mamba architecture. It enhances its ability to focus on the truly relevant context, leading to more robust and effective language models, particularly valuable for handling long-range dependencies and complex retrieval tasks, where filtering noise is key.
And finally, we come to a paper that's all about making large language models more efficient and accessible. NE4, it's a learned 4-bit weight quantization solution. What does learned 4-bit mean, and why is this so important for deploying LLMs, everywhere?
Right. What's fascinating here is that critical trade-off between model accuracy and efficiency. Quantization, in general, is about reducing the precision of a model's weights. Think of it as compressing the model, making the numbers simpler. This saves memory and speeds up how quickly it can make predictions, which is crucial for deployment. Now, NE4 is revolutionary because it's a learned 4-bit representation. This means it's not a fixed, off-the-shelf format like standard integer 4-bit int4 or floating point 4-bit FP4. Instead, the specific 4-bit representation is optimized for the actual distribution of weights in the specific model you're quantizing.
So it adapts the format to the model.
Exactly. And crucially, it doesn't require any time-consuming pre-processing of the weights or activations, which some other advanced quantization methods do. This significantly simplifies the entire deployment pipeline, just apply NE4.
So it's like a custom, high-quality compression algorithm tailored for each specific model, making it much smaller and faster without losing much quality, and it's incredibly easy to implement. That sounds ideal.
That's exactly the goal, and the results suggest they've largely achieved it. Their key contributions include this novel NE4 quantization solution. It consistently achieves higher accuracy, meaning lower perplexity, which indicates better language understanding than other standard 4-bit numeric representations like int4, FE4, and NF4.
Yeah.
You can see this clearly in their Figure 1, which shows perplexity across various Llama 3 model sizes. NE4 is consistently the lowest line, meaning highest accuracy. And it does this across a wide range of popular models, Llama 2, Llama 3, Mistral, Mixtral.
And how does it compare to methods that do require pre-processing?
It's very competitive, even with methods that do require that extra complex pre-processing. And they even show it's effective down to 2-bit and 3-bit levels. pushing the boundaries of extreme compression while maintaining surprising accuracy. Plus, it can be calibrated very efficiently using just a single curated diverse sample. And they've open-sourced TinyGem, a highly optimized GPU matrix multiplication library that implements NE4, making it readily accessible to everyone. So yes, NE4 offers a highly efficient and accurate solution for quantizing LLMs, making them vastly more accessible and deployable on resource-constrained hardware, like phones or edge devices. It really accelerates LLM inference for countless potential applications.
Wow, we've truly covered a remarkable range of innovations in this deep dive, haven't we? From, new AI architectures capable of genuine thinking through energy minimization to making models understand hours of video to even grappling with the nuances of machine bullshit.
It's been an incredible journey through the absolute cutting edge of AI research this week. We've seen advances in core model capabilities like reasoning and multimodality, totally new training paradigms like dynamic chunking and that incredibly efficient reinforcement learning for long videos, and even these critical looks at AI's emergent behaviors and how they might affect us. What stands out most to you from all these breakthroughs? What are you most excited to see develop next? Well, this weekly digest, as always, just reminds us that the field is moving at an absolutely astonishing pace. Each of these papers really, in its own way, pushes the boundaries of what's possible. And they're tackling crucial challenges in AI's development, everything from making them fundamentally more intelligent to making them more practical, reliable, and efficient. It's the whole spectrum.
Indeed. It really feels like progress on all fronts simultaneously. So, as you reflect on this deep dive, maybe consider this. If AI models are rapidly gaining these complex System 2 thinking abilities, the capacity for deliberate logical reasoning, and they have the power to understand vast multimodal data like hours of video, what entirely new ethical and societal questions might emerge that maybe we haven't even begun to fully grasp yet? What new exams, perhaps, will humanity need to prepare for? And how will we collaborate with these increasingly sophisticated intelligences to shape our future?
That is a profound thought. The journey into AI's future is really just beginning, isn't it? And understanding these fundamental advancements, like the one we discussed today, is absolutely key to navigating it wisely.
We certainly hope this deep dive has given you a valuable shortcut to being well informed on where things stand right now. Until next time, keep that curiosity ignited.